Welcome to session 2 of ViViMaT 2, the PhD sessions. My name is Stefan Peeters and I'll be your host again today. By the way, if you subscribe to this channel, YouTube will notify you when new content is uploaded. That way, you won't miss any of the interesting talks coming up in the next days. Our first speaker today is Stefan Peeters. He's a postdoc research assistant in the group of Clelia Righi at the University of Bologna. He got his bachelor's and master's degrees in chemistry at the University of Ferrara in 2015 and 2017. And in 2020, he earned his PhD in physics and nanosciences from the University of Modena and Reggio Emilia. I'm pretty sure I reviewed one of his papers last year. Today, he will give us insights into the tribochemistry of extreme pressure additives, right after this. Coatings is a peer-reviewed journal of coatings and surface engineering published online by MDPI on a monthly basis.
And now, extreme pressure additives.
Hello, my name is Stefan Peeters and I'm a postdoc research assistant in the computational tribology group of Professor Clelia Righi at the University of Bologna. Today I'm very happy to be able to present some of the results we obtained during my PhD and also some more recent results in the framework of our ERC project slide. So I'm going to talk about the tribochemistry of extreme pressure additives by ab initio simulations. So the materials typically employed to reduce friction can be divided into friction modifier additives that are introduced in liquid media and solid lubricants that operate in dry conditions. I am particularly interested in extreme pressure additives. So they are complexes such as ZDDP or MODTC that contain elements, sulfur and phosphorus, for example, able to passivate the sliding part. In fact, when these complexes are in tribological conditions, they can break down and release elements or molecular fragments that can passivate the metallic substrate or recombine into tribofilms. As you can see, there's a lot of chemistry involved at the tribological counter. But all these different transformations are difficult to monitor by experimental techniques because the interface is buried. And therefore, simulations offer a valuable perspective into the tribological phenomena. And in particular, quantum mechanics offer the possibility to describe chemical interactions because also the electronic degrees of freedom are taken into account, which are essential to describe chemical interactions. So our objective is to understand the effect of mechanical stresses on the tribochemical reactions. So our approach is to employ density functional theory, mainly in the pseudopotential plane waves approach, to describe the tribochemical reaction. We also employed a quantum mechanics, molecular mechanics, multiscale scheme, which is very useful because it allows to focus the computational power only in the simulation region where chemical reactions take place. So we use a variety of different simulation codes. For example, in Quantum Espresso we modified the Carparinello and Born-Oppenheimer dynamic modules. And our QMMM scheme is based on the coupling between Quantum Espresso and LAMPS. So the simulations we perform can be static, in which we describe the properties of the molecular structure, for example, electronic or vibrational properties. We can understand the interaction with metallic substrates, and also what is the effect of load on these additives. But dynamic simulations are also very important to understand the time evolution of the tribological system, to introduce the effect of temperature, and to better understand all the mechanical stresses, to include also sliding. So now I'm going to describe the theoretical characterization we have carried out for MODTC compounds. MODTC compounds, molybdenum dithiocarbamates, are a group of different chemical structures, like the one represented here, that are very important in tribology because they are known to reduce the friction of steel, but around 1 order of magnitude. So the mechanism behind the lubrication of MODTC relies on the fact that MODTC breaks down and it forms molybdenum disulfide tribofilms. So in our simulation here we consider small chains in the lateral groups of MODTC to reduce the computational cost. However, these molecules typically have longer alkyl chains, So one of the first mechanisms proposed to describe the dissociation mechanism of MODTC shows that the initial step of the decomposition takes place by breaking the sulfur and molybdenum bond. And then, after some steps, we obtain the beneficial MOS2 tribophene. Another study, based on vibrational spectroscopy, proposed that the first bonds to be broken are the ones between carbon and sulfur. So this is a debated issue in literature. However, the complexity of MODTC not only relies on the decomposition mechanism, but also on the quick oxidation that these complexes undergo. So we started our investigation by considering different fragmentation patterns of MODTC compounds. As you can see, for the isolated compound, the easiest way to break the molecule is between sulfur and molybdenum, because it has the lowest fragmentation energy. We must remember, however, that metallic substrate can indeed stabilize differently the molecular fragments, and so the picture can change. We then consider all the possible isomers obtained by exchanging the position of sulfur and oxygen. It turns out that the bridging position between molybdenum atoms in the compound is the least favorable for oxygen, while the ligand position between carbon and molybdenum is the most favorable. To better understand the effect of oxygen in this compound, we can vary the number of oxygen. And in fact, molecular structures with less oxygen atom and more sulfur are less stable than the ones with more oxygen atoms. So this calculation relies on the fact that sulfur and oxygen are exchanged on a metallic substrate. To better generalize this result, we built a stability diagram in which we vary the chemical potential of the sulfur atoms, so atoms that come out as a product in the oxidation reaction. So first of all, you can see that oxidation is generally favorable because both lines are below zero for a wide range of potentials, but also that double oxidation is more favorable than the single oxidation. Here, the chemical potentials range from a very unfavorable situation of the isolated sulfur atoms, and on the left we have a very favorable situation, which are sulfur atoms adsorbed on iron. And here the vertical line is our target material, MOS2. But we also considered vibrational spectra of these additives, and actually they are all very similar to each other. But we can find some diagnostic peaks, for example the molybdenum double bond oxygen stretching, which is found at 1000 centimeters to the -1. And this kind of simulations can be very helpful to ease the experimental characterization of these compounds. So now I'm going to discuss the dissociation mechanism of MODTC on iron. So to better understand the tribochemistry of MODTC additives, we designed quantum mechanics molecular mechanics simulations by employing a subtractive scheme. This approach is particularly useful because it allows to focus the computational power only on the region where chemical reactions take place. In the quantum region, energies and forces are calculated at the DFT level. The rest of the system is treated by classical formulas, which are not typically designed to represent the tribological system in this condition of extreme reactivity. So in these two movies, you can see two different simulations. On the left, we have a MODTC molecules with the oxygen atoms in the standard position, which is in the middle, the terminal position. On the right, you have an oxidized MODTC complex with the oxygen atoms in the ligand position. As you can see, there are some differences in the reactivity that can be well visualized by looking at these snapshots. Here on the top, you can see the initial conditions. In the middle, the systems after 1 picosecond, and on the bottom, the two systems at the end of the full dissociation, which happens at two different times for the two molecules. On the left, you can see, for example, that the standard molecules have central units that are not very well defined. The oxygen is in the middle, and also sulfur atoms are close to molybdenum, which is a different fragmentation pattern from the one predicted by static simulations. On the right, we have oxidized MODTC, where the central units have the correct stoichiometry to form MOS2, because the oxygen atoms have been pulled by the ligand units. And this is a very favorable situation to build the beneficial MOS2 tribophene. So as you can see, quantum mechanics, molecular mechanics simulations can be very effective not only to capture the catalytic effect of the metallic substrate, but also to distinguish the different tribochemistry of different MODTC additives. Of course, metallic substrates can be covered by passivating layers, and for this reason we consider iron substrate passivated by 1/4 monolayer of oxygen, a full monolayer of oxygen, and also 1/4 monolayer of sulfur. In all these cases, MODTC additives struggle to adsorb. Only very weak physisorption is obtained, even in the presence of high loads. And in fact, decomposition cannot occur because the molecular fragments have no space, have no free sites where to attach to on the surface. Now I'm going to describe mononuclear MODTC compounds. Mononuclear MODTC compounds are typically present in lubricant mixtures based on MODTC, but they are usually neglected. Mononuclear MODTC is presented in few patents and also in a recent study where the durability of mononuclear and binuclear compounds is compared. It is shown that mononuclear compounds have a longer durability. But what is the impact of the mononuclear compounds on the tribological properties of MODTC? So to gain some insight, we separated a commercial mixture of MODTC by means of flash chromatography, and we characterized all the relevant fractions containing MODTC. Here the most important ones are 7, 8 and 9. And here we carried out tribological tests to compare the friction reduction properties of all these fractions, and we also compare the results with the commercial mixture. So it turns out there is no fraction better than the reference, the commercial mixture, most probably because of a synergy between the compounds that are present in this fraction. So to better understand why, we carried out an extensive experimental characterization of these fractions, and it turns out that by mass spectrometry, the most important mononuclear structure is this one, with longer alkyl chain of course, and electron paramagnetic resonance revealed a particular electronic structure for this compound. All the ligand units surrounding the molybdenum atom account in total for 4 bonds, so 1 for the left unit, 1 for the right unit, and 2 for the double bond with oxygen. But EPR revealed that the oxidation number of molybdenum is +5, and the only way to combine the results from mass spectra and EPR is to consider mononuclear MODTC as a radical cation. Of course, neutral compounds can also be present in the lubricant mixture, and they might not be detected. And for this reason, we carried out our theoretical characterization by considering both the cationic and the neutral compounds. So the mononuclear radical cation has a much stronger chemisorption to iron and also less favorable dissociation energies compared to both the neutral compound and the binuclear structures. So here you can see, for example, the frontier molecular orbitals, and also the simulation can very well detect the localization of the radical electron on the molybdenum atom, and also it can be detected by the asymmetry of the spin components on the density of states. So now I come to discuss the interaction of ZDDP with lightweight alloys. So ZDDP is a well-known additive able to reduce the wear of steel contacts. And even though the tribochemistry of this compound is studied since many years, it is known in fact that it undergoes many different chemical reactions, both in solution and on the metallic substrate. There are still some unclear aspects on the decomposition mechanism, especially for lightweight alloys, which can be very useful for energy savings in the automotive industry. So as you can see from these two studies, ZDDP is not able to provide low friction in all cases. So here you can see there is high friction when ZDDP is used on alumina, while it is able to provide low friction when the tribological tip passes before on silicon and then on aluminum. On the right you have a similar example. In red you can see the friction coefficient when ZDDP is used on a magnesium matrix. In the middle we have two aged substrates, while the black curve represents the friction coefficient on an alloy based on magnesium and aluminum. So to better understand the tribochemistry of ZDDP on these lightweight alloys, we first characterized the properties of isolated ZDDP. We started from the structural properties of the DDP unit, So we found out that the trans configuration for the alkyl chains is more favorable than the gauche configuration. Then we move to the electronic properties of ZDDP, and we also consider different fragmentation patterns for ZDDP in analogy with what we have done for MODTC. It turns out again that for isolated compounds, the most favorable way to break in the molecules is by separating sulfur and zinc and leaving the sulfur atoms on the ligand unit. Then we consider different substrates. We first consider aluminium. The 111 surface is the most stable, and also we consider 001. And in both cases, you can see that ZDDP is not able to attach to the surface. There is only weak physisorption of just few tenths of millielectron volts. To compare, you can see that with iron, the molecules not only is able to chemisorb, but also decomposes, and so you have very strong chemisorption of around -5 electron volts. So I hope I was able to show you the power of ab initio simulations in describing the tribochemistry of extreme pressure additives. So to summarize, we have seen the effect of oxygen on the isolated compounds, the decomposition mechanism of MODTC on iron substrates. We have seen not only the catalytic effect of iron, but also the different tribochemistry of these additives depending on the position of oxygen in the molecules. We moved to describe mononuclear MODTC and their peculiar electronic properties that have an effect on their tribological performance, and also that this computational protocol can be adopted to describe the tribochemistry of different complexes, for example ZDDP with lightweight alloys. I would like now to thank my colleagues Paolo Restuccia, Gabriele Losi and Alberto Berlini, who helped in the calculations, my supervisor Professor Clelerighi, and also our external collaborators, Sophie Loeillet, Benoît Thibault at Total, and Professor Goswami at IIT Delhi. I would like to thank the European Research Council for funding, and also Stefan Eder and Carsten Gachot for this nice opportunity to present at ViViMaT. Thank you all for watching.